basically, I just want to wrap up because like we started from the dark matter, then we moved to programming. Now I'm going to have a little bit of something that is dark, not matter, and programming. So let's do it like this. I even later wanted to call the talk. I thought like, okay, it was like what, all shades of quantum or whatever. But then I thought like it should have been called something like from dark matter to black box. Sound like this, and then it should be like exactly the stuff about like coming from like physics to AI. But yeah, basically, let's first, because now we are discussing, yeah, like Kurt is unhappy about Grover, etc. Yeah, so like, do we really already have quantum advantage? According to Google, we always have it. So I mean, through all the years, what they publish, we always have advantage. The other one was on 22nd of October last year. So basically, it was already after our meeting in September of this group. But I like the idea. Again, so it might be, since Google never gives data, never gives code, etc., we would never know if it is true. Because like, but you know what? In Nature, so they always get publication in Nature. This is very important. So their publication always goes to Nature. Sometimes they are even on the cover of the month. But then it's written that data and code is available upon request. My request was never answered. So I mean, like I tried to request it several times, never works. Yes, unfortunately. Yes, unfortunately. Yeah, I mean, maybe maybe for that we anyway need Google machine in order to reproduce it. Who knows? Yeah. So, but at least, I mean, show me the code, show that you did something. But they have a verifiable quantum advantage. They were modeling 28 atom molecule. So as they claim that they have like 28 atom molecule, and they have like, you know, like for those who are not that much into details, basically we have like, it's one of the promising field of quantum that we're going to be able with quantum to make molecular simulation and discover drugs. Yeah, so like now when we had this, I mean, the other drugs, come on. So, but this one we can discover easily in the streets of Zurich. But for quantum, we just need another one. So basically, like now, for example, Andrea was mentioning during this discussion that generative AI is trying to cure cancer already for whatever years. Yeah, I think quantum is trying to create new drugs for even more. So I have heard it already for like tens of years, but still nothing. What's the problem? Because in order to do this, yeah, for example, you want to understand how different proteins bond with each other. Yeah, and there are like billions of possibilities of how it could be done. Yeah, and then you need to exactly like take your molecule and exactly see if the bonding would work. And saying that, okay, quantum, we have this parallelism, whatever stuff, this might work, but in reality, it's not about parallelism. In reality, it is about that you have like a huge matrix, huge Hamiltonian, yeah, that is kind of like representing how the system works, and you need to figure out the parameter of this matrix. So really, like all the stuff that is tried to be solved with quantum is about managing big matrices. Let's call it like this. So like all we're going to be today talking with me, it's about managing big matrices. And one of the ideas how Google suggests like to manage it, this is this OTOC new algorithm, but basically the major problem is that we get not just this advantage, but we get it verifiable. So it means that if we now run it on Google machine, and then we need to run it on IBM machine, the result going to be the same. Now it is not like this. So till now, like if we run it on machine with one noise system, then we run on machine with another noise system, results are different. But Google said that they run it on whatever many machines and everything works well. What I like is the idea of what they are trying to do. So how they are trying to make sure that the results are reproducible. Yeah, even though we don't see the code, but let's trust to Google that it is reproducible. So basically, they use the idea of sonar. So like this radio signal. So they first kind of set the signal. So it means that, okay, so for those of you who came today, like the new ones, no idea about qubits, etc., just qubits are, let's say, the neurons, and then have connection between neurons. That's it. This is what you need to know. So basically, this is quantum. So just the connections between the neurons are a little bit more interesting than in classical neural network. But the idea is the same, yeah? So you have input, then like you have some manipulation between them, and you have output. So here we have a quantum circuit, yeah, so several inputs, then the program runs, and they start with this set of qubits and run forward pass. So basically run the circuit and see like how this chaotic system works. Then they make a perturbation in a one single qubit. So they have a control perturbation, yeah. Basically they introduce how they call it butterfly effect. And then they are making the reversing of the signal. So basically, because quantum circuits, they are fully invertible, since it is a linear operation. Only linear operations are done. Then basically, we can try to backpropagate and see this initial state back with this little perturbation in a single qubit. And then they are trying to learn from this. So they call exactly this echo learning. So we are trying to see like this little difference. And in the end, they are kind of introducing it into their algorithm. So they are amplifying their signal with these echoes. And again, not that much information, unfortunately, only like this single Nature paper and couple of blog posts from Google without any clarifications. But they have like this short, let's say, GIF, that is not GIF now, but the stuff about like step 1, 2, 3, 4, how they do it. And we know from them what it was inspired with. By the way, anybody knows from which movie this picture is? Which? Batman? Dark Knight, exactly. I told you there's going to be something dark, not the matter, but there's going to be the Dark Knight. So like basically Batman, he used the technology of sonar in order to find Joker. Yeah. And by the way, I'm going to also then share the slides with you. So also I have them in Google Slides, and there I put some links to the description of the slides. There are going to be the link to the picture, to the paper from Google, and there are going to be also the links to maybe you don't know, there is now this series of cinema cinema showings from Pate, which is called Once We Love. So, for example, yesterday I went to watch The Dark Knight. So, like last time I have seen it in the cinema in 2008. And finally, after so many years, I thought like, come on, we have this talk today, I have to watch it. So yeah, I had to go to Rapperswil like late at night. So I came back hardly like at 2 a.m. Yeah, so there was a tough night, but not as tough as the algorithm from Google. So Google claims that we have this quantum advantage. Okay, let's try to trust them, though I would not. But what we can already trust, yeah, please. Yeah. Yeah, I mean, not dropouts. I mean, to some extent, this learning is quite close to what is, for example, was first introduced to cycle GAN, if you remember. So when first these generative adversarial networks appeared, and we were trying to understand how well they train, then basically we were doing this full cycle, yeah? And we were basically comparing like input to reconstructed input, basically kind of like this, yeah? So like, for example, how you can do in different language models still, when you are first making like forward translation, and then you are making a backward translation, yeah? And you are trying to understand like how close they are. I would say here, this is like this idea exactly of perturbation, signal back, and then you are seeing like what is the difference. So basically you're kind of learning the error pattern. Basically, this is what I would call it. Okay, yeah, maybe we can call it like this. So you are exactly trying, so through different steps, so for different qubits, so per each step you are using a single qubit, and then you are exactly trying to learn this error pattern. So it means that when it is executed on some, let's say, unknown machine, then we can see what error pattern this machine has and to correct it. So basically, when we then move a forward pass, we, let's say, have learned what is the error shifts happen on this exact device. Make sense, more or less? Yeah, no, but here that's why it is verifiable advantage. So I mean, like at least we now can verify it. So, but the rest is the history. Okay, good. So I mean, as I said, unfortunately, I could not run it myself. But what is important, I also prepared for you. If you wish, then I'm going to provide the link, a little repo for today's talk. And there I have provided for you like the couple of Jupyter notebooks. One of them is about verifiable advantage context, where you can see like little experiments on just to catch the idea of what it means to get this kind of the noise model. Okay, good. Then if we continue, like about what we can trust and do. Like, okay, with Google, it's not yet clear, but what it is clear with is, for example, with some, and I mean, what we now talk about, these are all such called quantum enhanced methods. So basically, we are trying to take this quantum circuit instead of, let's say, a neural network, and to provide some solution that would be then fully executed, for example, on quantum computer. And due to some cool things, it's gonna give us the better idea of what is going on. For example, one of the huge hype is called quantum anomaly detection. So I think like it was already through many, many years, and also many international banks, they were trying to use this idea with anomalies, basically because we have a time series. And usually we are looking for some anomaly inside the time series. So, I mean, like, of course, it could be just anomaly, basically, for example, among your client profiles. This also could be the case. But most likely you are looking, for example, into the thread of transactions, and then boom, something has happened, yeah? And it could be multidimensional. This is now just for visualization, but in reality, this is multidimensional. And this is, by the way, so Ian already today mentioned Penny Lane. This is a visualization from Penny Lane. Why I like Penny Lane more than Qiskit? They have nice features. They have a good designer. I think that they have hired somebody from Disney, if I'm not mistaken. So like he's making drawings for them. And this is what happens in quantum. What is the idea? Basically, you are, instead of just using this, I mean, the same idea as in all the machine learning time series models. Yeah. So like you are taking observation 1, 2, 3, you are encoding them. For example, this could be your encoder decoder system or whatever part. And then with some threshold, you are deciding if it is anomaly or not. Here, you are just making this encoding into this quantum state of like 0, 1, and then applying some quantum algorithm. Ideologically, I would say is pretty cool because in the end, you can make these entanglements. Yeah. So like now for others who are not yet in the topic, so the main power, let's say, that we consider in terms of quantum computing, algorithmic, machine learning, whatever, is these entanglements. So basically, this is kind of, I would say, if-else condition that we can introduce like between different nodes. And for example, if I now say that they both could have been like 0, 0, 0, 1, 1, 0, 1, 1 in the end, yeah? So if the result is only 0 or 1. If I introduce entanglement, it would occur that only results 0, 0, and 1, 1 are now possible. All the others, they could not happen at all, yeah? So this is kind of like, and they say they talk to each other, yeah? So like they say, like, hey, if you become 0, I also become 0, yeah? If you become 1, I also become 1, yeah? And then whatever happens, this is how it works. So it's sad that because of these kind of interactions, which are pretty hard to model in the classical neural networks. So like try to make these connections, yes, or try to, I mean, like try to Google like how to introduce if-else conditions being differentiable in the neural network. It's super complicated, yeah, I mean, like really try to do it. But in reality, in quantum, it works pretty efficiently, it works like straightforward, and that's why there are really sometimes improvements, but improvements of what kind of source? I'm gonna show you how it usually looks like. So first of all, they usually measure it against some regression. So this is like the first part. So quantum machine learning guys, they really enjoy saying that we are better than regression. I'm also better than regression. Yeah. So I mean, I don't need to be quantum for that. The second part is that in reality, if you're gonna, so I run it, I try to measure the training time, yeah? So I mean, like, look, regression took like less than a second. This one took like 278 seconds. So in reality, what we were now discussing, even having potentially less parameters, the thing is that the algorithm itself is so much more complicated that yes, in the end, it's gonna give you a better accuracy than the, let's say, for example, regression. But it's usually the question of trade-off, yeah? Because it occurs that, for example, now I can introduce here like a little bit more complicated LSTM model that's gonna be, for example, training not for 1 second, yeah, but for example, for 200 seconds, but which would have already on par accuracy. So this is very important to understand that there are these little manipulations that quantum machine learning guys really love to do. Yeah, so that's why when you say, for example, they are not honest, whatever, I would say that they are who are claiming these results. They are not honest. They are just not telling all the truth. I would say like this. So they're just hiding something. So like, I don't know, we were before like talking that, okay, I can also be like the fastest like man in the world, yeah, if I break the legs of Usain Bolt, yeah, for example, like this is super cool method. This is what they are doing, yeah, so this is quite close to this. Okay, so, but still, I mean, like this is quite an example of how the anomaly detection is done and where you can really see kind of an improvement that makes sense is, for example, when you have all these algorithms applied to Large Hadron Collider. So like guys that are doing this in CERN, they are doing, for example, this application of anomaly detection in the detectors, yeah, in the real detectors. And there, since the data itself has the origin of physics, and then they apply quantum kernels. So the same as classical kernels in SVMs, but just applied in a quantum manner. Then it occurs that this stuff really works. So, I mean, again, improvement, and here there is a different manipulation. Improvement doesn't cost the price of what was paid in order to run this algorithm. So yes, in the end, they get improvement in accuracy, and not against the linear regression. No, they get improvement against the state of the art. But it occurs that we need to burn like thousands of Swiss francs in order just to make this single shot of training that may be a little bit later. Yeah. So like when we are talking about like hardware is missing, algorithms are missing, I would agree with Ian saying that algorithms still are, let's say, more behind than hardware. So with hardware, I would say that we might be already quite close soon. Yeah. The only question is like, what would be the price? So meanwhile, because 3 years ago, IBM was pricing you $1.6 per second. Now it is $1.5 per second. Yeah. I would not say that price decreased that much. So, I mean, I still cannot do it myself because like really imagine that you want to train 1 hour. I don't know, maybe next Christmas. But yeah, definitely not now. So in reality, it means that there are some, again, applications, good use cases. As I said, there are going to be links in the presentation, so you can look into them, but they're quite limited and they're quite expensive, let's be honest. Now, what is unlimited and not expensive is quantum inspired. And the one that I was showing to you before, this was done by like one group of quantum inspired machine learning in CERN. And what I'm now going to be talking about, this is also kind of their thing that they work on. Imagine, like, this is, as I was promising, quantum neural network or quantum circuit would look almost the same as a classical one, just with the exception that now these are qubits, but not neurons, yeah? And now this is how we make connection between the neurons. So we just have a little bit more complicated connection. And I can run it as a single huge matrix, yeah? So I can say that this is operator U, or it occurs that I can decompose it into the series of connected small matrices. And this is, I would say, the stuff that is now making the main difference on the market of AI that I see from the quantum inspired part. Because like you can imagine like where we have like huge matrices, like in LLMs, yeah? So we really have like huge matrices, sequences of huge matrices. But for example, what inspiration we get from quantum? We have this operator, we can decompose it. And now imagine that for me, only this part matters in terms of final measurement. Yeah, so I want to know the result that comes from, let's say, these first two guys around them. In reality, it means that whole this part that is now gray, it does not have that much influence as this part. And to some extent, I can ignore this part. I mean, like why you see now two, because like this is how the measurement happens. So I mean, like you just, not the measurement, but you get the estimated value. So you basically have two matrices here. But for us, it's important that comparing to this picture, this part is neglected. And it still works pretty well. This is the main trick. So like we are getting these like two inspirations. That first, far away staying, let's say, neurons and connections, they might be not that much influencing us, yeah? And second, we need to understand which exact part we want to know the answer about, yeah? So that maybe we don't really want to know like all the answer, maybe we need just a part of the answer. Also, this is observation. So this is basically what I'm interested in. Yes. So like which part I want to observe. So like in quantum terminology. So, and now this is where the magic happens. We try to now apply it to classical tensors. So what we now have seen, it's called in the classical world, the tensor network. And if you ever have seen it, maybe have anybody used tensor networks? No, not yet. That's great. You see, you didn't come for nothing. So, of course, like for two previous gorgeous talks, and maybe tensor networks. So how it works, like in practice, tensor networks, these are not tensor neural networks, because you know tensors, they are like pretty much attached to neural networks, but tensor networks, it's something different. Tensor network, it means that, for example, if I have like a vector, yeah, and if I have a multiplication of vector by matrix, I know that vector by matrix, I'm gonna get a vector, yeah? But the thing is that I can introduce it as a graph, yeah? I can say that here is dimensionality ij, this is dimensionality I. I know from the linear algebra, I'm gonna have j in the end as the output dimensionality if I'm gonna multiply these two things. And then it occurs that I can come to the higher dimensionality and still continue the same idea. I would just be connecting with these dimensionalities, which matrices, or in this case, it's already tensor, yeah, which tensors I'm multiplying to which one. And this way I'm gonna create, yes. Exactly, it's usually gonna be like this, but this is the visualizer from Penny Lane. So he decided that he sees the world from this part. Yes, I mean, absolutely no reason, really. I mean, like we can draw it the other way. G is a matrix, V and W are vectors. So like this is the example of vector matrix multiplication. This is the example of tensor multiplication. So where we have like a more complicated tensor multiplication. And basically, in the end, we're gonna keep this idea that we can, as I said, we can decompose a single big matrix as a multiplication of different small matrices, which are then connected to each other in terms of tensors. Yeah, so these are tensors, and they are connected to each other via this graph, and they form in the end. So this is kind of a big tensor, but it is decomposed to the multiplication of the small tensors. And this is the idea that was taken like a couple of years ago, and it was tried to apply this idea that we have seen on previous slide, yeah, that maybe we can a little bit ease some conditions, and now I'm gonna show you how it works. So it works, not how, but first where. It works now in LLMs. So basically, there was a company that was called Multiverse, and Multiverse Computing, they were able to get like 215 millions, which I would also wish to have, for the groundbreaking technology of compressing LLMs by 95%. So what is their idea, what they're trying to do? They're trying to do exactly what we have seen on previous slides. And they have already pretty good, let's say, proof of the concept. That's why they got this 215 millions last summer. So I mean, like, it's not that. That's why I have checked before the talk. Meanwhile, not yet a second breakthrough. Yeah, so they have this proof of concept that gave them money. Maybe right now they're trying to work. Yeah, so you know, money needs time. But basically, what happens? I'm just leaving this slide for you if you want to read it at home. But just a basic idea for those of you, especially who are working in data science. I think it's a kind of cool inspiration of how you can do different things. So imagine you have a huge matrix, you can decompose it. So you have now the combination of the matrices, multiplication, tensors, let's call it tensors. Each of them has maximum 2 connections. This is like the, only under this condition, this stuff would work. And this is called this matrix product operator. So we just form these little matrices, and then we start the trick. We take each of 2 matrices, and for example, we see like, okay, now they have, like here it was 256 on the dimensionality where they bond, yeah, where they get multiplied. So it is said that this is kind of the information that can flow like from one matrix to another one. Yeah. Now, most likely, all from these 256, we do not require all of them, or maybe some of them are already correlated, or like whatever stuff happens. And then we can apply a trick from linear algebra and get the SVD decomposition in order, for example, to reduce this dimensionality, this bonding dimensionality between the matrices with the, let's say, some loss, obviously, of information, but not a significant loss of information from, for example, 256 to 32. It's very important that these guys, they were like experimenting around it, and they have figured out that, for example, this drop in dimensionality, this kind of order, this doesn't hurt a lot. So really, if you were able to decompose your like super huge matrix into these little ones, and now you are going like through all these possible combinations, and you are trying to even more reduce the connectivities, or how they call it, weakening the bonds between the matrices, then in the end, you just have these weakened bonds. So now instead of like these 256, let's say between each two matrices, we have 32 between each two. Now there is like a mathematical procedure of coming back to the original matrix. So like we can not only decompose into this matrix product operator, yeah, but we can take these matrices and create back our big matrix, but now it's going to be much smaller. So we have decomposed it. We have tried not to lose that much information between each two couple of matrices, and then we decompose it back. And now this W compressed is already used in our model. So imagine like when we track, for example, LLMs, they are like having many matrices. Like if you look at the transformers, for example, architecture, and basically these guys, if I'm not mistaken, they took some llama model. They were able then to reduce its capacity by 30%. So I mean, like the weight of the model, it was reduced by 30%, with only loss of accuracy on the like tasks that it was solving, like less than 1%. And I think it's pretty cool. So basically, you are getting like much lightweight model, yeah. So, and it is not this distillation as it is done classically, yeah. This is another type of distillation that in reality works quite well. And now, I mean, hoping that they have a lot of money, maybe they're gonna bring us even more. You see, they claim to have 95% of compressing LLMs. On the website, it's not said. Yes, please. Of course, yes. So this is very important. So I mean, like you train it, and then you apply this already post-factum. Yes, exactly. So this is all for faster inference. This is all aiming us for having faster inference without loss of quality. Yeah. Good. Other. You know what they say? Yeah, there is an implementation. I even tried it. It works. So I mean, they have an open source repo. I also attached the link. And I also provided like a little example of what they are doing in the repo that. I mean, of course, these are not like some pool data sets, but I mean, still, like. This is the case, then you can compare it very well, because it's not important for the text. I would say no. In general, you know, like why originally this idea of distillation has come from the big models, because a lot of connections, they are pretty weak by themselves. So I mean, like your matrices, they are quite, I would say, sparse to some extent, yeah. And this is the way. But in terms of sparsity, it is hard to say like, is it sparse? For example, this connection of 0.03, this weight, does it really matter or not? So there is no good way how to say that it matters or not. But via this, there are these mathematical procedures, yeah, where we also look at the variance loss. Yeah, so basically we can see at the variance loss, and via this SVD, this works pretty well. So guys, pure maths. Okay, so this is one thing that can work. And just to, as I said, okay, I'm already behind the time, but just to wrap it up. So I would say that, yes, please. Yeah, this is what I'm trying to say, that, okay, this is this slide, sorry. I mean, no. This is important to say that there is this huge bulk of methods that are quantum inspired. So because originally it was exactly this idea of looking at the quantum circuits and trying to figure out like these entanglements, the strength of entanglement between different qubits. But then it was migrated to this kind of like classical neural network part, and it occurred to work pretty well. So that's why I would say that quantum inspired, this is those of you who work in data science, I would say it's a good time to look into this part along with the physics-informed neural networks. So I would say physics-informed neural networks are those that I pretty much consider to be quite promising, and this part as well, because I can really see results not only here. I also touched the link to the project that is called TN4ML. This is Tensor Networks for Machine Learning, and this is developed by one group in CERN, and they also have this open source project. You can try to maybe replace some of your models with this part. So compression, optimization, pattern recognition. This is how I would maybe say where it makes sense to be used, yeah? Quantum enhanced, those of you who are researchers, you are welcome to do whatever you want with quantum enhanced. So that is like supposed to run on quantum, and which is supposed to be a quantum algorithm. So, but if you want to be then like fair enough, compare it to the state-of-the-art neural network, let's say, yeah, and then claim that, okay, you have like, because seriously, this stuff about having less parameters in quantum network, one qubit doesn't equal one neuron. This is very important to understand. And like the time to train neuron is much less that we see from practice than for training one quantum bit. Yeah. So that's why having this kind of claim that our model has 216 parameters, the quantum one, and your classical has 1,000. That's why we are 5 more times efficient. No. So this doesn't work. Either work at the exactly loss curve. So see how your loss curve is improving. Again, it might occur that, yes, your loss curve is improving, but the resources that you're going to spend, it's going to not worth it at all. So this is always about this fairness. But what I also find is important to mention that they can also, from my vision, work like in a collaboration. And for example, quantum inspired can like have a pre-processing and prepare the data for quantum enhanced, because really, I see the big issue with quantum methods that we do not have that many quantum bits, yeah, though they are really seem to be stronger than classical neurons. We cannot input a lot. That's why what people are doing, people are taking the original data, let's say 700, yeah, they are applying PCA. They say now they have 30, and now let's pass it to the quantum circuit. It doesn't work this way because you already broke all the properties. You already broke the initial properties of the data, and then you are trying to pass it to the neural network. But with this quantum inspired, if I would take, let's say, learnable quantum inspired preprocessor, I have a suspicion that I might be able to still keep the quantum properties of the data and then be able to run it on the quantum circuit. So let's see if it works, because this is like very ambitious and this is only in my head, but who knows like what's going to be tomorrow. And also, just about our group, I mean, in general, this is like a wrap up. I want us to get like more inspirations, you know, from different parts. And yesterday with Rudy, we were at PhD defense. So imagine guys claiming his topic is nuclear magnet resonance, whatever stuff. And then this is what we see. So continue talking about beer. Then like, what does ethanol spectrum tell us? So basically this was like the full presentation, like 45 minutes about alcohol. So in reality, guy, he really like took the spectrometer and he was like figuring out how lager, IPA and white beer differ between each other. So I would wish that we have more inspirations like this, you know, like, you know, not to have some boring stuff, but that we really have the inspiration from, let's say, beer, even if it is non-alcoholic as today at our event. Okay, yeah, but make long story short, I think this is like the end of our meetup, the official part. So